Today we're going to talk about exponential growth and decay, and this is really just kind of an intro to what we're going to be focusing on this unit, and that's differential equations. So exponential growth and decay. E to the x is an example of a function that is an exponential. It looks something like this. The idea behind an exponential function or exponential growth is that the more stuff you have, the faster it grows. If you think about, for example, this point right here, we don't really have so much of whatever that is. You know, it's pretty low on the y-axis, and it's not moving very fast. Its slope is pretty gradual. But up here, we have more stuff. We're much higher on the y-axis, and we're moving faster. We're growing faster because you can see our slope is much steeper. So there's a way to describe this as an equation, and that is y prime is equal to ky. So what that really means is the rate of change of y, that's the y prime, so how fast y is changing is directly proportional to, that's where the k comes in, y. So how fast y is changing is directly proportional to how much y we have. So you can think about it this way: the more y you have, the faster it changes. The less y we have, the slower it changes. Now this was actually used to create some formulas that you're really familiar with, that you've used before in previous classes, and I want to show you how that was done. So first of all, y prime just means the derivative of y. We've talked about the fact that there's other ways to write that. We can do dy over dx, or I'm going to do dy over dt, since we're really talking about things changing over time. So just rewriting that equation, just replacing y prime with dy over dt. Both just mean the rate of change of y. Now if you notice, our variables are kind of mixed up. K is just a constant, just to be clear about that. It's called the constant of proportionality. You don't really have to remember that name. It's just important to know that K is just a constant. But we've got variables mixed up here. We've got a y on the left side in the dy, and we've got a y on the right side, and we've also got t on the same side as y, so our variables are mixed up. So we want to separate them. That's the first step. So I'm going to multiply both sides by dt. That gives me this. The next thing I want to do is divide both sides by y, because now my variables have been separated. Everything that has a y in it is on the left side. Everything that has a t in it is on the right side. Well, we have a derivatives. We want to get back to the original. If you look back, we started with y prime. We want to get back to the original. So I'm going to take the antiderivative, or the integral of both sides. dy over y should look familiar. It's a familiar form. It's very similar to du over u. It's the derivative over the original, and that is the natural log rule. So natural log of the absolute value of y. Now k is just a constant, so you think about it just like it's a 3 or a 5 or whatever. So the antiderivative of k would be kt, and of course we need to put plus c. And just so you know, we only put c on the right side of the equation. In a sense, both sides have one, but basically if you've got two constants on each side, then if you combine them, there's still just a constant. So we'll only put a c on the right-hand side when we do this. Now we don't want to know the natural log of y, we want to know what y is. So we're going to raise both sides to the power of e, or make both sides powers of e, and that will cancel out the natural log for us. So the e and the natural log get rid of each other, leaving just y on the left side, and on this side we have e to the kt plus c. Now that equation might not look familiar to you yet, but it actually is. Okay, now I want you to think about the properties of exponents with me for a second. X squared times x cubed is equal to x to the fifth, and that's because when you multiply two exponents together, when you multiply two things with exponents together, you add the exponents. Now we almost always go this direction with this property, but we're allowed to go both directions. After all, they're equal to each other. So if you notice, this has an addition sign in the exponent, so I can rewrite this way. Again, if you're multiplying two things with exponents, you can combine them by adding. So it should make sense that this going this way can give you that. So it stands to reason that we can go either direction. Okay, now e is just a number. Remember, you can plug it in your calculator. It's just 2.71 or something like that. And c is just a number, it's just a constant. So if you have a number raised to a number, it just gives you a number. So instead of calling that e to the c, I'm just going to call that capital C. And we normally write that out front like this. And this is a formula that you've used before for exponential growth and exponential decay. For bacteria or radioactive decay or population growth, or if you just use the same form but different letters, it's really just the interest formula. So that's where this comes from. Now what I just did was actually solve that differential equation. We're going to talk more about how to solve them later. I don't want you to so much worry about how I solved it as much as I want you to make sure you understand that this equation, the idea that the rate of change is directly related to, or directly proportional to, the amount of stuff we have, is directly related to this equation. In fact, you may often in a AP question or even in the book or on our test see this equation up here, and instead of doing all the work that I just did, you can just now memorize or remember that it ends up down here. There aren't going to be any others you need to memorize the results of or anything, so don't worry that you're going to have to memorize a whole lot, but this is one that's important to know. It's important to link these two things, so you know automatically if you see one, you know the other's involved. So that's our introduction to exponential growth and decay, and that lets you see how calculus is actually what helped us derive the formulas that you've been using for a long time.